Hello and welcome to this key tutorial. Today we're going to be looking at the basics of MPLS technology. We're going to look at the concepts of MPLS, the terminology of MPLS, and see how MPLS provides solutions in service provider and mission critical networks today. MPLS is a great technology and it's getting a lot of interest today, but it's not so new. It was actually defined way back in 1998 by the Internet Engineering Task Force. You may know already that MPLS stands for Multi-Protocol Label Switching, and each of the parts of its name are really important, as we'll see shortly. It's currently in use in IP-only networks, but in theory, MPLS can carry many other network protocols. And it enables high performance traffic forwarding and quality of service traffic engineering. Now, a typical requirement for MPLS transport might be in the retail sector, where constant use of point of sale devices requires transaction data to be carried rapidly to the processing data center. Today, many applications for MPLS are within the VPN, or Virtual Private Network. The diagram will show a couple of applications. Firstly, for establishing a point-to-point E1 leased line over the VPN in what we call a pseudo-wire. And then secondly, for building private LAN services where we can interconnect multiple LANs which are based at different sites. So, why multi-protocol? Well, simply put, MPLS doesn't care what underlying protocol is used. It could be Ethernet, or SDH, or PDH, or even ATM. It simply maps onto the Layer 2 protocol and provides a common, fast, efficient transport method over the packet switched network. If you're asking where does it fit into the OSI 7-layer model, well, the answer is it squeezes in somewhere between layer 2 and layer 3. So let's call it a layer 2.5 protocol. So in the transport part of the network, MPLS routers do two very important things. Number one, they map onto any layer 2 protocol below. And number two, they check the IP packet above as it arrives at the doorway of the transport network and sends it on its way in the most efficient predetermined route it can. So now let's have a look at how it does that. And as we'll see, it's all to do with labels. Before we go any further, let's take a quick look at the difference between routing and switching. When an IP router receives a packet, it has to find out which network it must forward it to and out of which exit port. So it scans its routing table to see if there is a match with, first of all, the longest network mask. And if there is no match, then it tries again with the next longest network mask, and so on. It can only forward the packet when a match has been found. And so there's often congestion, because it's a time-consuming task, and it can add significant delays to the forwarding process. But switching is different. A switch holds a table containing a simple list of input port IDs and packet reference IDs, and also output port IDs and new references to be applied to the outgoing packet. All the entries are of the same type and importance. And this simple process makes for much faster forwarding of the packets. MPLS uses the best of both routing and switching. And we'll see shortly that the routing decision made for one packet as it enters the MPLS domain can be used for a whole class of similar packets. They receive a class label that is simply read and replaced at each MPLS router. And the device that makes MPLS so efficient is called the label switching router, or label switch router, or LSR for short. It's a combination of a switch and a router. And in reality, LSRs are often classical IP routers which have been MPLS enhanced in a software upgrade. So where we previously had lots of IP routers in a packet switch network, in the MPLS domain we have lots of LSRs instead. The job of the LSR is to accept an incoming packet and forward it out of the correct port as quickly as possible. A special function of the LSR is when it's at the edge of the MPLS domain, and then it's called an edge LSR, or more commonly an LER, a label edge router. Now I want to take you through the process of what happens to a packet as it enters the MPLS domain, makes its way through, and then exits at the far end. So first of all, the packet arrives at an ingress label edge router. It arrives from the IP domain, and the LER, it checks the layer 3 information on the packet, then it checks its lookup table and finds a reference called a forward equivalence class for that particular packet type. The label for the class is then added or pushed onto the packet, simply a number, and the packet is then forwarded into the MPLS domain. Now this label is actually held in a special header called a shim header. A shim is just another word for a thin spacer, like a metal washer, and it's inserted between the layer 2 and the layer 3 headers of the IP packet. The full format of the shim header is shown in the diagram here. Now back to our packet. Inside the MPLS domain, the packet arrives, there it is, at the label switch router. The LSR checks the packet's label in its label information base and swaps it for a new number, and then forwards it on into the MPLS domain. Finally, the packet arrives at the edge of the MPLS domain at an egress label edge router. The LER removes or pops the label and then forwards the packet on according to normal IP forwarding rules. Now clearly one of the advantages of MPLS routing over normal IP packet routing is that the path across the network is established even before the packet starts its journey. For every forwarding equivalence class that we talked about earlier, we have something called a label switched path, a predictable route, which has been put in place by one of two protocols that is running on all the LSRs in the network. This is either Label Distribution Protocol, LDP, or Resource Reservation Protocol Traffic Engineering, RSVP-TE. And by the way, all LSPs, label switched paths, are established unidirectionally, one direction only. The return path may take a different route. Okay, let's look at one last example. In this MPLS network, we have 4 LSRs, including 2 LERs, an ingress LER on the left and an egress LER on the right. Initially, the predictable label switched path is established using the MPLS protocol. Then a standard IP packet arrives from network A on the left at the ingress LER. It assigns the packet to an FEC, that's the forwarding equivalence class, and pushes label 16 onto the packet. The packet continues to an LSR, which checks the entry for that label in its label information base. It finds a new label 27 and swaps the labels. The packet continues to the next LSR, which does the same thing and swaps the label for 33. Now remember, the FEC hasn't changed, only the label changes. Finally, the packet arrives at the egress LER, which pops the label off and forwards the packet without a label to network B. In the next video in this MPLS series, we'll take a look at some of the MPLS monitoring tools and MPLS protection options and the evolution of MPLS towards MPLS TP, which many are seeing as a real carrier-grade alternative to SDH. Thank you for watching this key tutorial.